Okay, the red light's gone on, so let's make a start. It's a bit noisy there. So I hope you all had a good weekend, not too much study. Let's just continue off from where we left off last Friday. So this is the last slide that we had, where we had been introduced to the density of states. So I just want to draw your attention, because we're going to use it again today in the lecture. G is what we represent as the density of states. And it's a little bit fiddly, this lecture, okay? So I'll go through it, and probably when you get home, maybe go through yourself and just make sure you can follow sort of all of the steps. It's very fiddly little equations, okay, but it's not necessarily hard, but they're just a little bit fiddly. So G is equal to V, the volume of our unit, L by L by L, 2 pi squared 2 me, mass of the electron, h bar squared to the power 3 over 2, square root of the energy, which gives you this dependence here, because the energy is along here, and this is G. Okay, so for now, just remember this quantity here, because we're going to use it shortly. Oh God, where's my keyboard? Okay. So what we're going to use is Fermi-Dirac statistics, which I think you know, the Fermi function and so on, but this tells us how the electrons are going to be populated at a finite temperature. That plot that I had before, as you saw, just kept on going and going and going. It didn't tell us when to stop populating it with the electrons, okay? We just have n electrons, and it doesn't tell us how it changes as a function of temperature. Okay. So this should be kind of familiar to you from statistical physics. Am I right about that? Can you put your hands up if you've seen all this before? Yeah, okay, good. Okay, so we know that the probability, this is your f function for 0 temperature. Let me just put the form of the thing here, okay? And so the probability of a state being occupied is 1 up to a certain point here. And this is the chemical potential, which we represent by mu. And it's an energy, and for temperature T equals 0, the chemical potential is called EF, the Fermi energy, or sometimes we call it the Fermi level in this area. Here I've just put a couple of values of the Boltzmann's constant for you. You may often have seen it in joule per Kelvin, but quite often it's convenient to have it in EV per Kelvin. So as I said, at T equals 0, all of the states, all of the electronic levels of our box are filled up to the highest state, and this is called the Fermi energy. And if you have some temperature, some finite temperature, then this function gets this kind of form here, where we get some states becoming unoccupied, and they become occupied here above the Fermi level, okay? So these states have been depopulated, and some states have become populated, because they get excited and they can jump up to the energy levels higher up. You can think about it like this if you want. These are all of your energy levels, spin up, spin down, spin up, spin down. This might be the Fermi level, and if you have some temperature, say, for example, this electron has been depopulated and it gets excited up into other levels. Okay, so that gives you a visual, way of thinking about that plot that I just showed you, what's really going on in the system. Okay. So this is a bit messy slide, but I want to just, you're probably very familiar with it, but I just want to go over it again. It doesn't hurt. So this is our Fermi function, or Fermi-Dirac distribution, if you like. We can rearrange that to get just the difference in energy on one side. And this difference in energy corresponds to, okay, there's EF, that's our reference energy, and the energy here is just some E along this axis here. So to get a feel for how it behaves, if we consider a value of the Fermi function to be 0.1, okay, this is your Fermi function, here's 0.1, so you're going to cut here. Then this has been drawn for two temperatures, okay, where the blue curve is T1. You can see it's a much sharper corner. That corresponds to a lower temperature. The higher the temperature, the more smeared out this function becomes. So if we consider 0.1, which I've drawn on the green line here, then that cuts, say, the red curve. We are considering the larger one, temperature here. At this point here, which is some energy E, and when you work that out, that equals 2.2 kBT. So the distance in energy, or the difference in energy from E to EF, is 2.2 kBT. Okay. Then you can do the same thing for 0.9, just to get you a feel of, you know, the energies involved here. Okay, this is 0.9, and it will cut the energy here, and that will be a negative energy difference, and so you'll actually get E minus EF being equal to minus 2.2 kBT. So what's the point? The point is to show you that for a given temperature, the energy difference between, for example, the values that we considered here is of the order 4 kBT. That should be a kBT, okay? So it's actually quite small, as we'll see on the next slide. Okay, and what's important here is these are electrons. When they are excited by the Fermi energy, we can treat them like an ideal gas, and so they obey the Maxwell-Boltzmann distribution. Okay, that's kind of an important point. Makes them very easy to treat. Anyone want me to go back, or it's fine? Okay, so how does this function help us to see how the density of states become occupied? Okay, remember we had here G of E, the density of states, could go on and on and on. And then we have the Fermi-Dirac distribution that tells us how many electrons are occupied and at what temperature. Okay, if we're given temperature, we have a certain occupation. All below the curve here, of course, the states are occupied. Above here, there's zero occupation. So when we make the product of these two functions, it basically says all the electrons are occupied here, and then the Fermi-Dirac distribution will cut off the electrons of particular energy. Okay? So this shaded area represents the region of electronic states that are occupied by electrons. This is important, so remember this, okay? Just telling, very fundamental, important for this course. So for you to kind of get a feel, you may do this for homework. Okay, there's the answer. Just make sure you get it. Evaluate the Fermi function for energy kBT above the Fermi energy. Okay, it's very trivial, but just it's a good exercise to do it. All right, now here comes a little well, not quite so complicated slide, not too messy. So the next one's a bit more messy. But okay, so what's the point? The point is we're trying to make a theory that's better than Drude, okay? And so what we can do is consider a more accurate description for the heat capacity. This is what we're aiming for. If we get a more accurate description for the heat capacity, and we get a more accurate description for the velocity of the electrons, remember Drude underestimated and overestimated those, but there's a cancellation. We are getting a more accurate value of those two things, so we are, in this model, going to shoot for a more accurate value of the Lorentz number. Remember, the number was quite good in Drude, but it was off by a factor of 2. What we're going to see is with this approach, we get a much better description. So we need a much better heat capacity. which we're trying to do here. And we're going to use the Fermi velocity, which we'll talk about shortly. Okay, so let's think about it. We've got our plot here. What we want to do is estimate the number of electrons that become excited at a particular temperature. Why? Because those are the electrons that will contribute to the heat capacity of the material, not the electrons that are all populated, just the ones near the Fermi level. Okay? So we need to estimate the number of electrons near the Fermi energy. In particular, we want the energy of the number of electrons near the Fermi energy. Okay? So what we're going to do is, first of all, the electrons are going to be assigned an energy just from ideal gas theory. So every electron will be given an energy of 3 over 2 kBt. Okay, that's just from ideal gas theory. So if you consider, so that's the energy. Now we need to know the number of electrons that are excited. Okay, so how do we get that? We're going to consider a rectangle, okay, as an estimate to, if we can figure out the volume of that rectangle, that will give us the number of electrons that are excited in this region near the Fermi level. So the volume of the rectangle is just kBt. That's just the energy along here that we talked about. That's your length along there, if you like. And the height is just the value of the density of states, okay, at the Fermi level. So there's a box. The box is equal to that. Okay? So this expression here, kBt times the density of states at the Fermi level, gives us the number of electrons here, and every electron will be given an energy of 3 over 2 kBt. And once we've got the energy, the heat capacity is obtained by just taking the derivative of the energy with respect to time for constant volume. Okay? So you can see here you've got two t's, t squared. One of when you differentiate, the 2 will come down. We'll get rid of that 2. And so you'll end up with 3 kb squared t times the density of states at the Fermi level. Hooray! Okay, so that's good. That's a that's a nice estimate of the heat capacity. It is only an estimate because we're just sort of approximating that as a rectangle box. It's pretty close, but it's not exact. And so what I've put here, there's quite a lengthy derivation in Ashcroft and Mermin, where the actual precise value is given by this equation here. I'm not expecting you to derive that. It could be interesting to go through the working if you like, but I'm just putting it here for extra reading if you want to see how it's derived. Let's just compare them, okay? Both have the density of states at the Fermi level, G, T, T, kb squared, kb squared. It's very close, okay? This is a 3. This is pi squared over 3. Pi squared is what? 9 point something, okay? Divided by 3, it's going to be a little bit over 3, but it's very close. So this is, in fact, quite a good, approximation to the actual value. Good. Okay. So we've got this expression here. We're going to be working now on the next slide with the precise values. It's got the pi squared on 3. So let's go to the next slide. And yeah, what are we trying to do in the next slide? Okay, this is kind of a weird number. Density of states at the Fermi level. We want to replace G of E of F by a better expression that we can evaluate. Okay, so in the next slide we're going to replace this function with something else. So how do we do that? Now, I've put a few extra bits and pieces on this slide compared to what might be on Canvas. This will go up on Canvas anyway later on today, but just a few more. It's very messy, but okay, let's see. So we started with this from the previous slide, okay? And at the very start, remember I drew your attention to the expression for the density of states at any energy E. Remember at the start I pointed that out? That's this expression here. Okay. Remember also from the second lecture we had derived the expression for the Fermi energy, 3 pi squared n over 2/3. So these are two important equations that we start with in getting a better expression for G of E of F. Okay? So, first thing we want to do, what is the first thing we want to do? We want to replace, we can replace this expression here, 2m of E of h bar squared 3 on 2, using this equation here. So we can just rearrange this expression to get this line here. Okay? Just comes out after a few manipulations. Then we can substitute this into here. Okay? So then we get this expression here for G of E being equal to 3n, total number of electrons, 2 times the Fermi energy, E, your arbitrary E, divided by the Fermi energy, all to the power half. So it's just a neater way of writing it. Okay, so now we need G at the Fermi level. Okay, and we've got a nice expression for G now, so we just substitute for E the value of E at the Fermi level. Okay, so you basically all you need to do is put this to an EF. EF divided by EF is just 1. Okay, so this thing will drop out because remember we want it at the Fermi energy, and you end up with this expression for the density of states at the Fermi energy equals to 3n divided by 2EF. Okay, so that's the height, if you like. Remember our density of states function went like that. At the Fermi level, there was some value of G. It's now given by this expression here. So, so if you want to figure out the number of electrons that are excited, remember that's what we wanted to figure out, the number of electrons that are excited, we just now multiply this function, G of E of F, by KBT, because that's that rectangle I'm talking about. KBT was just along the horizontal, and the vertical part of the rectangle was just the density of states at the Fermi energy. So this quantity here is the number of electrons that are excited due to that application of temperature. Okay? It's quite important here. The number of electrons, 3 kBT, n divided by 2EF. So, with respect to the total number of electrons in your system n, you can just divide by n and you get this. So what this tells you is the fraction of electrons in your particular metal that might be characterized by a Fermi energy at a particular temperature. So if I said, okay, you've got aluminium, your Fermi energy is, I don't know, 11 eV. Figure out the proportion of electrons that are excited at a temperature 500K. You could just use this. Okay? So it's quite nice. I mean, it looks a little bit fiddly, a bit messy, but it's quite straightforward. So what's the point now? Now we've got an expression for G of EF. Here, we just substitute that into this equation to get rid of this term, which we didn't really fancy. And you obtain this expression here. Okay? The gamma, we've just pulled out that pi squared over 3. You can easily put that back in there. Okay? So this is basically the derivation of the heat capacity for the free electron model that we're talking about. Okay? And when you have a look at it, you can see that it's dependent on temperature, and it's a linear dependence. When you actually work out the values, you will find that it's a factor of 100 smaller than the Drude result. And that's good. Remember that the Drude theory overestimated the heat capacity by 100. This now gets rid of that overestimation, so it's a much better approximation. So that's good. Fine. Fine, fine, fine. Excellent. So we can just plot that and have a look at it. And so this is the heat capacity of the solid. This is what we've just calculated. We have only considered electrons so far, right? And remember, our heat capacity we found had some, factors in it, but it was proportional to temperature. And so we are dealing with the blue line here so far. In a real solid, the heat capacity is due to electrons, sure, that we've just considered, but it's also due to the lattice phonons, right? That's going to contribute strongly to the heat capacity, particularly here. If you're in high temperature, you can see that the heat capacity is going to mainly due to the lattice vibrations. But when you're at low temperatures here, the electrons are the dominant contribution to the heat capacity. Okay, good. Now just to go aside a little bit and a bit more about just some, remember we were evaluating some of these things. Remember we have this is just a summary slide. Give you some idea of the actual values that these Fermi properties are equal to, okay? We have here, okay, this is actually for an example of potassium. The concentration, if you like, of the valence electrons is 1.4 times 10 to the 28 meters cubed. Remember I said it was always sort of like in the ballpark of 10 to the 28. Potassium's only got one electron, so it's 1.4. It's not that big. But that's your n, if you like, okay? Your little n. And your little n is equal to big N over 2, right? Concentration, number divided by volume. And when you substitute in the values, you'll find that the Fermi energy for potassium is about 2.12 eV. Remember on the previous slide we had some of these values again ranging from, I guess, this number up to 11.63 for aluminium. So they're always of the order of sort of a, say, 2 to 11 eV or so for the Fermi energy. You can calculate the Fermi wave vector here, and you will get a value of around about 0.7 inverse angstroms, okay, for this potassium. You can calculate the Fermi velocity, okay, momentum, P, at the Fermi level divided by the mass, and you'll get about 0.86 times 10 to the 6 meters per second. Remember, Drude underestimated the velocity, so this theory gives you a greater velocity, more like realistic values. And you can also work out the Fermi temperature. Remember, energy at the Fermi level is equal to Kb times T, F. So you can just invert that and get an idea of the Fermi temperature. It's always going to be something of this order of magnitude, say something times 10 to the 4 Kelvin. Okay, it's a big number. Okay, and it doesn't, of course, reflect the temperature of your solid, because the temperature of your solid is due to lots of things, not just the outermost electrons, but these outermost electrons here have a very high Fermi temperature. Okay, but there's a lot more electrons in your atoms than just the outer ones. Okay, so what have we got? We have got a better Fermi velocity with the free electron Sommerfeld model, and we have got a better heat capacity C of V. So now we want to see what does the Lorentz number look like from the Wiedemann-Franz law. Remember this? Okay, remember we had thermal thermal conductivity divided by electronic conductivity equals a constant L times the temperature. And this was the expression for the thermal conductivity. This was the electronic conductivity. These are the two aspects that we have now that are new, okay? The velocity and the heat capacity. So basically, when you substitute in our new values for V and C, we get this expression here. On the next slide, I'll show more detail, but this is what we get for thermal conductivity divided by electronic conductivity. This is your pi squared on 3 that we saw before. And basically, a few things cancel out. When you make this division here, you end up with kb squared over E squared times T. And the value of L, when you work that out, is about 2.45 times 10 to the minus 8 watt ohm Kelvin to the minus 2. Okay, so remember with the Drude theory, this was about, it was either 0.9 or 1. It was half that of the measured ones. Now we've got a really nice value, 2 point something. Okay, so that's much better than Drude. And, okay, so this is what we got with Drude. Okay, when we put in, I think we had the average Maxwell-Boltzmann velocity and a different specific heat. This is what we got from Drude, okay? Just bringing this back for you to look at. But now we have this different thing here. Okay, you see the structure is the same, kb squared on E squared, kb squared on E squared T. Everything's the same except for this prefactor here. This is about 1.5, where this is about 3 point something. So this approach gets you that factor of 2 better. Okay, so this is just telling you which values just reminding you which values we use to obtain this. Remember, we have the Fermi velocity and our newly derived heat capacity here that we just derived, putting it into here. So you should do that, okay? When you get home, make sure these equations are right, okay? It's good practice for you, and you'll, you know, become more familiar with the topic. Okay, remember we had these numbers here. This is at temperature, room temperature. This is the values for your Lorentz number that were measured, 2.2.2.2 point something. Okay, there was one that was a bit higher, and now this is with the free electron or Summerfield model, we get 2.45. Okay, so it's much better. It's quite surprising, actually, the agreement. So that's all that I'm going to talk about for now about the the Summerfield model. We're going to just summarize a few things. Okay, of course it's got some problems still. We have only assumed 1 electron per atom, right? So lots of atoms have, of course, many more valence electrons than 1. It cannot explain optical spectra, okay? The electronic band structure of real solids are much more complicated. This is probably quite well for like the potassium metal or the sodium metal that actually has got 1 electron, and N is a free electron like metal. But for anything like semiconductors or complicated insulators, it does not perform well, as you should expect. The specific heat, as I said, it does better than Drude. The specific heat is actually still, off by a factor of 10, on average, I guess. And of course, it can't explain magnetism. We've only got 1 electron in this model. And it doesn't take into account electron-electron interactions. So this is kind of a summary of some of the shortcomings of the free electron model. Because you can imagine you've got all these electrons in reality, in your atom, and then interacting with the electrons in the other atoms. There's going to be interactions between the electrons, which aren't included. More information about this, of course, is in Ashcroft and Merman, Chapter 3, if you want to fill yourself in a bit more.
Excuse me, Julie was saying that the textbook that you recommend was available online.
Yeah,
Is
yeah.
that in the library?
It should be, yeah. I could get access to it and download all the chapters, so I hope you can. If you have trouble, yeah, let me know. Yes. Okay, so what are we up to now? Okay, here I've just put a little bit of sort of summary revision about what Drood and Summerfield, or Sommerfeld, however you want to call it. Okay, so what I've put here is some things that you might like to, when you're revising for this, these are some of the questions you might like to remind yourself. For example, I should say at this outset, you won't have to derive detailed equations like I've presented there, but you should be familiar with them. So you may like to discuss Drood and the formulas for DC conductivity. What kind of information can you obtain from the Hall effect? Remember we talked a bit about the Hall effect? Okay, you don't have to derive it, but you may like to look at the derivation of the thermal conductivity in the Drood model. What is the Wiedemann-Franz law? Lorentz number, and so on. I don't know if I need to read these all out to you, but what is the difference between Drood and Sommerfeld model? What are the typical values for the Fermi temperature, Fermi velocity, and so on? And the expression for the density of states that we talked about. Okay. Made a little summary here of some of the main equations, which I won't bother going over. And a description of some of the additional and limitations of the free electron-like model. Okay, I won't go over those because you can read them yourself, and I've already mentioned them. So basically, we need a more accurate theory, and we're going to get to that, of course, later on in this course. Band theory. Okay, so what I'm going to do now, just bear with me. I'm going to have to change over onto another PowerPoint slide. Okay, I think we just start the next one, which is, we're going to have a little break. We're not going to go straight on to band theory because I feel like we should discuss first a bit about solids. Okay, there you are. This is a fairly qualitative next few slides. Okay, so what are we interested in? We are interested in solids. Okay, so crystalline solids, as I mentioned before, that's what we're going to be dealing with. Nice and ordered, well-developed theory for them, where the atoms and molecules are arranged in a repeating pattern here. A high degree of order, regular periodicity throughout the entire volume of the material. Okay, so what's interesting is obviously you start here with the actual atomic positions. They may be arranged in some kind of order. This is kind of like in the square lattice, you can see. And when you generate a large chunk of that, okay, you end up with the square. And even for the macroscopic crystal, you often, the actual shape of it reflects. This is a square shape. It reflects, on the atomic level what's going on. Same as here, right? Down at the atomic level, very small, you have these kind of arrangements. And when you actually grow the larger crystal, very often it takes on the shape of the atomic scale arrangement of the atoms. Okay, we're going to just talk about some various kinds of solids. Okay, polycrystalline solids. Have some of you met these before? Okay, polycrystalline is defined such that it's made up of smaller single crystal pieces. Okay, so if you look at this structure here, it's a polycrystalline solid, and within each of these, what are called domains, it may have a different kind of structure or orientation to the ones neighbouring it. And they are separated by what are called grain boundaries. where at the grain boundaries the atoms may have a totally different atomic geometry, and often grain boundaries can dictate various properties of materials, like hardness of a material. If you measure the hardness of a material with an indenter, where you apply a force into it, very often the grain boundaries can dictate what kind of hardness you measure, and other properties. Yeah. What else? Okay, the ground boundaries are typically 100 to nanometers to 100 microns in diameter. And if they are very small, like very small regions of single crystal material, then those are called nanocrystalline. Okay, I think that's fairly straightforward what a polycrystal is. Amorphous. Okay, what are amorphous solids? Obviously, they're non-crystalline, and they are made up of randomly orientated atoms with respect to each other. You can see there's no real ordered structure here. They're kind of random. So amorphous materials, for example, amorphous silicon, plastics, and glasses. Amorphous silicon is quite successfully used in solar cells and so on, but we are really not going to treat them here, okay, because the theory of them is not that well developed. But you should know about them. What else? Molecular crystals. Here, these are really quite interesting structures. These are buckyballs. But the buckyballs can actually come together to make a solid here. Okay, so you can see that these are made of carbon atoms, 60 carbon atoms. You can get all different, sizes of buckyballs here. This is 61. And they come together, held together by van der Waals forces, which we'll get to talk about shortly. Also here you have molecular crystals where, you have these, basically they look like molecules, don't they? Okay? But they are held together by some kind of forces. It's probably van der Waals force. It might be some, could be some covalent bonding going on. But what you can see is overall, they can still form an ordered structure. You can see quite nicely these hexagonal kind of cells here. So these kind of structures can also be described using the models that we are going to study here. Okay, what else have you got? Liquid crystals and polymers. Okay, so these are some kind of little crystals, but they behave a little bit like a liquid. They are free to move around, and under certain conditions they will become oriented in a particular way, and they become actually ordered. Okay, polymers, like this just looks like a long string of atoms. When you blow it up here, you can see it's quite a complicated structure here. Again, we are not looking at these kind of materials right now. Okay, so what we're going to focus on now is just talking about the different kinds of bonding between atoms. Okay, I think some of you have probably heard about all of these. Ionic bonding, covalent bonding, metallic bonding, hydrogen bonding, and van der Waals bonding. Okay, now when you've got a number of atoms that come together to form a solid, it's the outermost electrons that are involved in the bonding. And what makes a particular structure is when the electrons bind together in a certain way that the total energy of the system is lowered. Okay, otherwise it would not form that structure. So there must be an energy gain by the bonding for the structure to actually form that material. Otherwise it's not going to form. So the cohesive energy is one measure of how stable a structure is and whether or not it will actually form in reality. So the cohesive energy is defined as if you can calculate the total energy of your solid in whatever structure you are considering, and so you've added up the contribution from all of the atoms, and then if you subtract off the energy of the atoms in free space, when they're not bonded to anything, then that's defined as the cohesive energy of your material. Okay, so we start quite simply here. Imagine that you have got, say, two atoms quite far apart, and we are looking at the interatomic potential between the two of them. What you'll find is you can describe it as two terms here. One is the attractive term here. So this is energy or potential along here. The lower it is, the stronger it is, okay? And there's also a repulsive part, because you can imagine you're bringing two atoms together, and if you push them too close together, there's going to be a strong repulsion from the electrons in the cores, okay? So you're going to get this repulsive part going up here, and the actual resulting potential may look something like this. Okay, this is a typical kind of shape for a solid. Goes down gradually, be some minimum at the bond length that the system has here, and then highly unfavorable if you try to push it too far. And if you plot the force that corresponds to the red curve, the potential, you will find at the equilibrium position there should be no force. Okay? The force goes to 0. Because if there was a force, then the atoms would move themselves a bit closer or a bit further apart to find that equilibrium geometry. So in a very simple description, you could have the attractive term just described by some constant over r, which is the distance between them, to some power, plus a repulsive part r to some other power where n is greater than n. This is a bit like you might have for describing van der Waals interactions, either with an atom on a surface, a rare gas atom perhaps, or for two atoms that are very weakly bonded together. Okay. Ionic bonding here. Okay. The typical example is sodium chloride here. Okay, there you are. And it has a rock salt structure. This is called a rock salt structure. The sodium atoms here represented by the little spheres here, and the chlorine by the large spheres. So, the sodium atom has one electron in its outermost shell, and it basically donates that to the chlorine atom here. So the chlorine atom becomes effectively negatively charged, and the sodium atom is effectively positively charged. And in the ionic bonding, the bonding is achieved by the electrostatic force. Okay? So it's just positive and negative charges. That's the way ionic materials are held together. Okay. Yes, we'll do a couple more slides here, more on ionic bonding. So if we just want to consider how much the energy contributions to forming the sodium chloride material, what can we consider? This is very simple sort of treatment, okay? It's not a full quantum mechanical treatment at the moment. But how much energy does it cost? Okay, you start off with a sodium atom, you start off with a chlorine atom. And first of all, you have to ionize the sodium. You've got to pull that electron off it. And that's called the ionization energy, is 5.1 eV. So we're taking that electron off the sodium atom. It doesn't really like it that much, but it's not such a high value. And then the so-called electron affinity of chlorine is 3.6 eV. So the chlorine will gain 3.6 eV when you put that electron from the sodium onto it. So, if you like, the net energy cost of creating sodium chloride is 1.5 eV per pair. And that's just an explanation of what I have said there, okay, about the ionization energy and the electron affinity. So, okay, now we've created our ions. Okay, we've got the sodium plus and we've got the chlorine minus, and that's cost us, what was it, 1.5 eV per pair. But we get a huge energy gain, right? And so we can estimate that energy gain by calculating the Coulomb energy minus E squared, electron, over 4 pi epsilon 0, and A is the lattice constant separating them. So when you calculate the gain that you get from bringing these two ions together, you get about 5.1 eV per pair. Okay, but so we had to pay for the cost of creating the ions, which is 1.5 eV. So the net energy gain is 3.6 eV overall. Okay, so that just gives you sort of the order of magnitude feel of why it's good and how you can actually build sodium chloride from sodium atom and a chlorine atom, because you will get a significant energy gain when you put it in a solid like that. Okay, so keeping now to sodium chloride. Okay, this was just a molecule. We just considered two atoms on the previous slide. So what about building the whole solid here, okay? So what we're going to do, if you can put yourself here, you're a sodium atom, and we've already created the sodium atom. We've already created the ions. Okay, we've paid for that. We're going to consider the energy gain from your surrounding neighbours. Okay, so from the next 6 chlorine neighbours, here you are. We're going to get an energy gain from the 6 chlorines. 1, 2, 3, 4, 5, 6. Okay, so that's why we get the 6 here. This is an energy gain. However, so we're going to add up the contributions from the atoms closer, a bit further away from the sodium atom where you are. So you've got an energy gain from the chlorines. What about the other sodium atoms a little bit further away in the next shell, shall we say? The closest shell was the chlorines. The next closest shell is more sodium atoms. So I'm not going to draw them all, but you can add them up. There's 12 of them. And that will be a repulsive contribution to the energy, okay, because they're two like charges. And the distance will be a bit greater because they're a bit further away, so the energy per atom will be smaller, okay, because the distance is a bit further away. So you get the idea. You can go out and out and out, adding up the contributions. If you go out to the third ring, I don't know, way down here, you'll get another attractive interaction between the sodium and the chlorine. And there's 8 of them, and they're a bit further away again. So you get this extra positive term here. So you get an attraction, repulsion, attraction, and you can keep on going, and it will converge to. So you can probably stop after a certain number of shells. So eventually the series converges, and we get for one ion, remember we were the sodium atom sitting at the front, at the middle, basically that number converges to minus 1.748, and that's a Coulomb interaction. And this factor here, the 1.78, this is called Madelung constant. Okay, you may have heard of that. And it's unique for, particular ionic crystals, and it also depends on the particular atomic structure that you have. But for sodium chloride, we have about 1.748. Okay, I'll just finish with one slide because I know you have to go and I have to go. So we were just one atom here at the center, considering the interactions with the other ions. But if we want to consider for 1 mole of sodium chloride, then we can multiply by Avogadro's number here. And because we were just considering the sodium atom, but it's for per sodium and chlorine atom, for 2 of them, we can multiply by 2. And when you're adding up these contributions, imagine you're doing this for each atom, you can overcount by a factor of 2, so we have to divide by 2. And this will get you a value of 8.61 kilojoule per mole. And this is what we call the lattice energy. And it compares, not too badly with the experimental value. 776 kilojoule per mole is the experimental value. But it's not a bad estimate for this kind of very simple description of the solid. Okay, I think I'll leave it there. I think we've managed to finish, yes, we have finished the sodium chloride example, and we'll continue this again tomorrow. Okay, but leave it there. I've got to run to a tutorial, so unfortunately I can't, take any questions just now.